Okay, everyone. This is it. This is our last week. 2 days. That's it. That's all we have left. And then our final exam. 2 classes. That's it. Our final is next Wednesday. All right? All right. We have a lot to do. So what I'm going to do here, we did not quite finish 8.6. Now, we did finish 8.6 in the sense of I had shown you all the theory, but we hadn't done enough examples for you to really get a feel for it. But because of our time crunch, I'm going to move to 8.7 right now, and then if we have time, I think we will have time, at the end of class, I will go back and do a couple of examples from 8.6. Let's just see how this goes. All right, so y'all ready? Yes? Y'all feeling all right? Okay. This is probably my favorite section out of the whole book, I think. Taylor and Maclaurin Series. So last section, 8.6, what we did was we said, hey, if we have a function, so this was last section, we said, hey, let's say we have some function, and I don't know, I gave you a couple of examples, but like that. The question was, can we convert it into a series, right? That was kind of like our goal. Can we get it to a series? And what we saw is that we can, so long as the function looks a certain way. As long as it looked like 1 over 1 minus u, we could do it. And then we had to maybe tweak this a little bit. Yes? Yes. Okay. So, is there a way to do it in general for any function? And that's what this section is about. This section is about taking a function to its power series using a formula. All right, so I'm going to give you the formula, but I'm going to derive it first. So first, let's agree with one thing. A power series, by definition, is this summation, c sub n, x minus a to the n, right? And we said that a power series, we're interested in its, only when it converges. So I'm saying here, let's suppose that we have a radius of convergence that's greater than 0. So we actually have an interval where this function is defined. Okay? Then can anybody here, for a free A in the class, you don't have to come to the final. I'm kidding. See, I got your attention though, didn't I? I got your attention. Can anybody tell me what one piece of this formula is the piece that actually dictates, like, how do I say this? What is the one piece of the formula that is different between each function? So I've given you one function that has a power series, right? I give you another function that has a power series. What is the one piece of this formula that changes from function to function to function? And what part of it doesn't change? Does that make sense? Doesn't. The c sub n. That's it. Look, the only difference, if this is the general formula, the only thing that's really relevant to us is this right here, right? Those numbers are the only thing that changes from function to function to function. You're always going to have x minus a to the powers in every single one of them. So the question becomes, is there a way that we can actually come up with the formula that would generate those constants in front? Like, can we come up with that? All right? Do you understand that? So here's how we do it. It's actually pretty sweet. We're going to take our general function. Here it is right here, right? And I'd like for you, just for the sake of following along, just tell me what the first derivative of that function is. So the derivative of that's 0, right? Okay, that's a constant. It comes for the ride. Derivative of this? 1. Okay, so we get c sub 1 plus, now we did this last class. I was showing you, we came up with a formula for the derivative, didn't we? Okay, but that's not quite what we're doing here. What about this one? When I take derivative here, 2 comes out, c sub 2, x minus a, right? I'm going to do a couple of these because you need to see a pattern here. One more. Okay, we agree? That's the derivative. Now, check this out. This is brilliant. Not my idea. What is the first derivative evaluated at the value of a? So if I ask you to plug a into the first derivative, what do you get? You're replacing x with a. So what do you get? C sub 1, right? So C sub 1 is f prime of a. You all with me? Because this is going to be what? Like if I plug a in here, 0, 0, 0, 0, all that's left is that constant. Okay? All right? Let's just put this on the back burner for now, all right? C sub 1. So this right here, right? This right here is the derivative of the function evaluated at a, right? Okay. Now, let's take the second derivative. What's the second derivative of this function? So take the derivative of this, okay? Let's see what you get. You get C sub 1 derivative, right, is 0. Okay, derivative of this? 2C sub 2 plus, now derivative of this one. 6, right? Because the 2 comes out. I'm not going to write it as 6, though. I'm going to write it as 2 times 3. C sub 3. X minus a to the first power. Plus, what's the next one going to be? Derivative. 4 times 3, right? Or 3 times 4. I'm going to write it as 3 times 4. And then C sub 4. X minus a to the second power. Second power, right? Okay, next one. Plus 4 times 5. C sub 5. X minus a to the third. Plus dot, 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 right? What do you think I'm going to do with that now? Evaluate it at a again. So what is the second derivative at a? 2c sub 2, right? Let's try one more. I think I'll do it right in here. Is that all right? I'm going to write down what I have so far on the side here. The first derivative at a is c sub 1. The second derivative at a was 2c sub 2. All right, now let's do our third derivative. So the third derivative of this function would be the derivative of this right here, right? Okay, so derivative of 2c sub 2 is 0. Okay, derivative of this? 6. I'm going to write it as 2 times 3 c sub 3. Right, that's that. What's derivative of this one? This is a critical one right here. 2 times 3 times 4, right? 2 times 3 times 4. C sub what? 4. X minus a. This next one will be 3 times 4 times 5. C sub 5. X minus a squared. Plus dot, dot, dot. And what am I going to do with that? Evaluate it at a again. What's the third derivative at a? So this gets killed off, that gets killed off, everything else gets killed off. All you have left is 2 times 3 c sub 3. Y'all following this? Sure? So let's write it down here. The third derivative at a is 2 times 3 c sub 3. Let's do one more, okay? Just one more. For the next one, we need the fourth derivative, right? We have a different notation for that because you don't want to be doing all these primes, right? So you do f and you do in parentheses 4. That means the fourth derivative of x. If you don't write this, okay, that means you take the function f of x and raise it to the fourth power. That's different than this, okay? So you put the 4 in parentheses. That should have been covered in Cal 1, but if not, now you get to see it. All right, so the fourth derivative is the derivative of this one, right? Okay, derivative of that is 0. Derivative of this, 2 times 3 times 4, c sub 4. And then check out this next one. 2 times 3 times 4 times 5. C sub 5. X minus a. And then I keep going, right, with this. Plug in a into this, and you get the fourth derivative at a is 2 times 3 times 4, c sub 4. There's a pattern over there. Do y'all see it? Just to see that we're seeing the pattern, what would the fifth derivative at a be? 2 times 3 times 4 times 5, right? C sub 5. And so on and so forth, right? So we have this general idea here right now. That if somebody gives you a function, right? Any function, say someone gives you a function. Here you go. Something you've seen in the past, sine of x. And you want to come up with sorry, I'm calling this something I haven't defined it. And you want to come up with its power series, right? Then all you need to know are what the constants are. So we said, well, can we find a formula for the constants? And I think we have a formula here, don't you? Let's see if we can't figure out the formula is. Right now, it looks like if we take the nth derivative, right, and we plug a into it, we get what? So I'm trying to see if you can see from this pattern what the nth derivative at a would be.
Yeah, 2 times 3 times 4 dot 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 anything.
It would be
N c sub n.
not quite n. What's 2 times 3 times, like 2 times 3 times 4, 2 times 3, 1 times 2, 1. What is that? N
That's not factorial.
factorial. Isn't it n factorial? Right? Look, what is 2 times 3 times 4? Well, 2 times 3 times 4 is really 1 times 2 times 3 times 4, right? The 1 is there, you don't need to write it. And that's 4 factorial. So that's 4 factorial, that's 3 factorial, that's 2 factorial, and that's 1 factorial. So the factorial is dictated by the derivative, right? And then what's the number next to it? C sub n, right? C sub n. And weren't we looking for a formula for that? Yeah, so look, just divide by n factorial and you have a formula. There it is. That's the big daddy right there. This is given a function, you can always find the constants for its power series by using this formula. Which means that you need to be able to take successive derivatives of the function, right? And evaluate it at a. Now, we have one particular constant in here we have not looked at. Like, this worked for C sub 1, C sub 2, C sub 3, right? We think it's going to work for everything else because of the pattern. But what about C sub 0? Does the formula work for that? So let's just try it. According to our formula, this would be, C sub 0 would be what according to our formula? C sub 0 should be equal to the 0th derivative of the function at a over 0 factorial. Now, the 0th derivative means don't take the derivative, all right? So this is just the function at a, and 0 factorial by definition is 1, all right? So this is just f of a. So shouldn't, if we look at this expansion right here, right? If we plug in a, this is 0, 0, 0, right? Which leaves c sub 0. So shouldn't c sub 0 be equal to the function's value at a? Like, that's what we just said. If you plug a in, this all goes away, right? So if I go f of a, we should get just this. So the formula actually works for all n. All right? Okay. So now we define the Taylor series. All right. Given a function like that, right? Let me put the theorem up here. Theorem says, and this is the theorem that defines what's called a Taylor series. Of a function f at a, all right? Here's what it says. If you have a function f that has a power series expansion. In other words, if you have a function that we can expand into its power series, then f of x will be equal to the sum n equals 0 to infinity of the nth derivative at a over n factorial x minus a raised to the n. And this is where, with the radius of convergence like that, okay? So you see this new formula right here, there's really not a huge new part to it, right? This is just what we just came up with a formula for, right? That is what we formerly called the C sub n, right? Now we have a formula for C sub n. All right. Now, this is a Taylor series, all right? This section is about Taylor series and Maclaurin series. So I'm now going to define a Maclaurin series. Maclaurin series is just a specific example of a Taylor series. It is just Taylor with a equal to 0. Have y'all ever heard this before? Like, this is a rectangle, right? Have you ever heard that a square is just a specific example of a rectangle? Right? Like, to be a rectangle, you have to have certain properties, like you have to have right angles in here, and then the sides have to be parallel. But a square satisfies all the conditions of a rectangle, right? So this is just a specific example of a rectangle. A Maclaurin series is just a specific Taylor series. It's the Taylor series when a is 0. So how would our formula change if I'm telling you that a is 0? Sum n equals 0 to infinity. What? Pardon? Yeah, it'll just be x to the n, right? But also, this will be what? F prime, the nth derivative, at 0. So you can replace this with 0, all right? Over n factorial x to the n. So look, it's just that formula with a replaced with 0. So a Taylor series, you can have a be any number, all right? And that, remember when we do a, it moves the function left and right. But if you want to look at a Taylor series centered at 0, then you're basically looking at a Maclaurin series, all right? We good? All right, we're going to start our first example with Maclaurin series because they're easier to do. And then we'll do Taylor series, all right? Now, I want to give you a goal. For those of you who came in, I guess on time, but maybe a little didn't quite hear me say, I'm starting with 8.7 today. At the end, if we have some time, I'm going to go back and do some more examples from 8.6. But I wanted to start class with a new topic and just kind of get right into it, all right? So I want to tell you what our goal is. All right, this is my goal. It's going to seem crazy. Have y'all ever seen this before? Or did I show this to y'all?
Oh, yeah.
I did talk to y'all about this?
Yeah, you brought it up.
Like the most beautiful formula in math. People say that's the most beautiful equation in mathematics because it has all these different properties in it. Let's just look at it real quick. It says e, which we're familiar with, right? Raised to the imaginary number I times pi plus 1 equals 0. All right, and then let's not get into why people say this is the most beautiful thing, but that's argued to be the most beautiful equation in math, all right? Now, doesn't this really mean that e to the I pi has to be -1? right? Just move 1 over, right? And that's, okay, I am going to prove this to you today, right? We're going to prove that that's true. If we prove that's true, we're going to prove that's true, right? Okay, that's my goal. Now let's see how we're going to get there. First thing we're going to do, first example, find, and just remember, this is going to be the end goal. I'm not doing this right now. This is the end goal, all right? Find Maclaurin series for f of x equals sine x. Hey, how's it going? All right, we're going to find the Maclaurin series for sine. So the way we're going to do this is we know that no matter what, it's going to have x to the n in it, right? No matter what. All Maclaurin series are going to have x to the n. This is the part that's going to be the thing we need to pay attention to, all right? So before I start trying to write this formula out, I want to see if maybe I can't come up with a formula, something that tells me what the nth derivative at 0 would be. So think about it this way. If I plug in 0, right? If I plug in 0, then you're not going to take the derivative, right? Right? And then you're going to plug 0 into the function. So that means don't take the derivative of that and then plug 0 in. So what would you get? Sine of 0 is? Sine of 0 is? 0. Okay. All right. Now, then if we plug in 1, what would happen? We take the derivative, right? First derivative? First derivative of that is cosine, right? And then plug 0 into that. Cosine of 0 is 1. And then we would do the third derivative and then plug in 0. Understand? So what I'm going to do over here is start listing out what the derivatives are first. So what is the 0th derivative of the function at x? Not at 0, but at x. So what's the 0th derivative? Sine x, right? Okay. Now, what is the first derivative of the function? Cosine x. Okay, what is the second derivative of the function? Negative sine x. What is the third derivative of the function? Negative cosine x. Okay, what is the fourth derivative of the function? Back to sine, right? And now the pattern is going to repeat. 0th derivative, first derivative, second derivative, third derivative, fourth derivative, fifth, sixth, seventh, right? Y'all okay with that? Okay, so tell me what I get now when I actually take the 0th derivative and plug 0 in. So first I took the derivatives. Now I'm going to see what happens when I plug 0 into them. So we erase the sine of 0 with 0, right? Okay, next one, this is going to be cosine of 0, which is 1. Next one, negative sine of 0, 0. This one, negative cosine of 0, which is negative 1. Next one, we're back to 0, right? 0, then 1, then 0, then negative 1, then 0, then 1, right? And that's what's going to happen. Y'all with me? Okay, so let's try and write out this power series. So I know it looks like this, right? I know it looks like this. Now, for this first example, I think what I'm going to do is I'm going to write this out. If I'm using the formula, if I replace 0, right, in here, I get the 0th derivative at 0 over 0 factorial x to the 0. That's me replacing all my n's with 0, right? Now I plug 1 into this, plus the first derivative at 0 over 1 factorial x to the 1, plus the second derivative at 0 over 2 factorial x squared. Am I going too fast? Or is this okay? A little bit? I know. The third derivative at 0 over 3 factorial x to the third. I'm going to keep going. Fourth derivative at 0 over 4 factorial x to the fourth plus dot, 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 right? Y'all see what I'm doing? I'm just rewriting the formula. Now, let's plug everything in. So what happens when I actually go and look at what this piece was? So what was this piece? That was 0, right? So that's going to be 0 over 0 factorial x to the 0. Okay, that's just going to be 0, but I'm going to put it down there. Next one. The first derivative at 0, right? Was this one? That was 1. So we're going to get 1 over 1 factorial x to the first power plus now the second derivative at 0. So here was the second derivative. At 0, it's 0, right? So this is 0 over 2 factorial x squared plus third derivative at 0 was negative 1. So negative 1 over 3 factorial x cubed plus fourth one was 0. So 0 over 4 factorial x to the fourth. Any questions on that? Am I kind of blowing you out of the water here? I'm sorry if I am. All right, I need to erase this because I need to keep going right here. Let's see if we can't figure out what the rest is going to be. This is where the pattern starts repeating, right? So what's the next one going to be? 1 over 5 factorial x to the fifth plus 0 over 6 factorial x to the sixth plus negative 1 over 7 factorial x to the seventh plus 0. Yeah, we could keep going, right? Do you get the idea, though? Okay, plus dot, dot, dot. My markers suck. Let's see if any of these are good. I thought I had some fresh ones there. This one looks pretty good. Okay, let's try these. All right, let's clean this up because that looks like a disaster, doesn't it? Okay, let's clean this up because there's a lot of zeros in there, isn't there? Okay, so this is now, let's see here. That's gone, right? This is just 1 over 1 factorial x. Next one, this is gone, this is gone. This marker sucks. Okay, next one is minus 1 over 3 factorial x cubed. Right, that's this one. That one's gone. This one, plus 1 over 5 factorial x to the fifth. You see, instead of the negative 1 on top, I'm just making it a minus. Okay, what's my next term? Minus 1 over 7 factorial x to the seventh plus, we don't have it written, but it should be plus 1 over 9 factorial x to the ninth. Let's see if you really get it. What's the next one? Minus 1 over 11 factorial x to the 11th plus dot, dot, dot. You get the idea? Okay, now, that is the power series. Sorry, that is the Maclaurin series for sine. This is it right here. This is the Maclaurin series. Now, did I mention last time how we had talked about sine back in pre-cal? They say sine is an odd function, cosine is an even function. All odd powers of x. It's not coincidental. This is actually how we define odd and even. If you do a Maclaurin series for a function and you get all odd powers, well, it's an odd function. If you get all even powers, it's an even function. If you get mixtures of both even and odd, then it's neither odd nor even. All right, so this is, let's see if y'all can do this, sum. Can you rewrite that as a formula? Let's see, what is it? Let's start at n equals 0, okay? To infinity. Okay, so what's happening? We have alternating, right? Starting with a positive. So negative 1 to the n plus 1. Okay, everyone agree? That'll give us the alternating that we need. Okay? All right, then you're always going to have 1 over something, 1 over something, 1 over something. So what is it? 1 over... Yeah, this is going to be odd numbers, right? 1, 3, 5, 7, 9. So you make odd numbers using 2n plus 1 or 2n minus 1 or something like that. We're going to be starting at 0, though. So we want 2n plus 1, right? Plus 1. I'm running out of room here. Let me move this over just a little bit. Get my dots in there. Dot, dot, dot equals sum n equals 0 to infinity negative 1 to the n plus 1, and then we said times 1 over, what did we say? 2n plus 1 factorial, right? Because if we start at 0, that'll give us 1 factorial. Then we plug in 1, we get 3 factorial, so on and so forth, right? Then x to the same thing. We have odd powers, right? This is 1, 3, 5, 7. So it's going to be the same thing that the factorials did. So 2n plus 1. Bam, there it is. If you look in the back of any good book that has a series in it, that will be what is written for the Maclaurin series for sine. The idea here is that if you got your calculator out, if you type in sine of 2 on your calculator, you would get an answer, right? You'd have to type it in. That answer would be the same answer you would get if you plugged in 2 here, 2 here, 2 here, 2 here, 2 here, 2 here, and had your calculator calculate that out. In fact, that is exactly what your calculator is doing when you type in sine of 2. It is using its Maclaurin series to get the answer, all right? But it stops somewhere, okay? It stops at a certain point. That make sense? Okay. All right. Good, good. Let's do the Maclaurin series for cosine. I'm just going to, for the sake of having it, I'm going to write over here sine x equals, oh man, this marker's terrible too. That's why they're in here. You do? Have good, oh, I might need one. Hold on. So I'm going to put over here, this one's pretty good. Sine x sum n equals 0 to infinity, negative 1 to the n plus 1 times 1 over 2n plus 1 factorial, x to the 2n plus 1. All right. Now, next example, find Maclaurin series for cosine x. F of x equals cosine x. All right. So, same thing. We need to come up with some way of generating what these derivatives look like, and we're going to be plugging 0 into them, right? I'm going to do that over here. So this right here, it's like I'm doing 2 columns, okay? First column, I'm doing basically what's the nth derivative at x, and then over here it's going to be what's the nth derivative plugging 0 in, all right? So first, the derivatives. What's the 0th derivative of cosine? Cosine, right? What's the first derivative of cosine? Negative sine, right? Second derivative of cosine. What? Negative cosine x? Third derivative of cosine. Sine x. And now when we get to the fourth derivative, we're going to be back where we started. Now, fortunately for us, the 2 functions that I've done so far are what we call periodic, which means they start to repeat themselves. The pattern repeats themselves. In general, that doesn't happen, all right? We will deal with that. We're going to have to see that sometimes it's a little harder to figure out what's happening over here. But with this, it's nice. All right, so what is the 0th derivative at 0? Cosine of 0. 1. Why am I plugging 0 in? Because it's Maclaurin series, right? Always 0 in a Maclaurin series, all right? If this is a Taylor series, then they would have to tell us where they want us to look. So then the derivative would not, you would not be evaluating at 0, you'd be evaluating at a, and that might be a little harder. Okay, so now, what's the first derivative at 0? 0. Second derivative at 0? Negative 1. Third derivative at 0? 0. And then I think the pattern's going to repeat now, right? We got 1, 0, negative 1, 0, 1, 0, negative 1, 0, and so on and so forth. All right. So let's do our Maclaurin series now. I'll put the Maclaurin over here. just so we have it. Maclaurin looks like this, sum n equals 0 to infinity. Nth derivative at 0 over n factorial, just x to the n. So let's start with n as 0. So cosine of x is equal to, starting with n equals 0, we do this, right? So the 0th derivative at 0 was 1, right? 1 over what? Plugging in 0 over there. 0 factorial, right? Which is 1. And then x to the 0. Yes? Plus, now the next one is the first derivative, right? Because I'm plugging in 1 for n. So this is going to be 0 on top, 1 factorial, x to the first. And then what's the next one? Negative 1, so I'm going to put plus negative 1 over 2 factorial, x squared. Plus 0 over x, not x, 3 factorial, x cubed. Do you notice where all the zeros are? They're on all the odd powers of x, right? And all the ones are on all the even powers of x. Okay, next one, plus 1 over 4 factorial, x to the 4th. So we're right here now, right? This is where we are? So plus 0 over 5 factorial, x to the 5th, and then plus negative 1 over 6 factorial, x to the 6th, plus dot, dot, dot. Let's get rid of all the zeros, right? So this is equal to, what's this right here? 1, right? This is 1, 1 over 1, x to the 0 is 1. So this is just 1. And the next one is minus, because it's a negative, 1 over 2 factorial, x squared, plus 1 over 4 factorial, x to the 4th, minus 1 over 6 factorial, x to the 6th. What's the next one? Plus 1 over 8 factorial, x to the 8th. One more. Minus 1 over 10 factorial, x to the 10th, plus dot, dot, dot. And into a summation, sum n equals 0 to infinity. We have alternating, don't we? Starting with positive 1, right? Or positive. So negative 1 to the n, right? To the n, because we're starting our index down at 0. So when we plug in 0, we get negative 1 to the 0 is 1, so that'll be positive, right? And then what? 1 over, what? Not n factorial, because these are even numbers, right? Basically, you could look at that. Remember, that's 0 factorial. So it's like 0 factorial, 2 factorial, 4, 6, 8, 10. So we need to start at 0, right? 2n what? 2n factorial. In parentheses, factorial. So if you plug in 0, you get 0 factorial. You plug in 1, you get 2 factorial. Plug in 2, you get 4, right? 6, 8. And now x to what power? 2n again. Bam. There it is. That's the Maclaurin series for cosine. So I'll put it over here. Cosine x equals sum n equals 0 to infinity. Negative 1 to the n, 1 over 2n factorial, x to the 2n. There we go. We good? Sure?
Just for concept.
Yes.
The 2n factorial you have to put in parentheses because if not, it's 2 times n.
That's right. Yep, this has to be in parentheses because if you write, let's say, what's 2 times 3 factorial versus 2 times 3 factorial, right? This means 2 times 3 times 2 times 1, but this means 6 times 5 times 4 times 3 times 2 times 1. Right? They're two different things. And what we want is this number to be generated first before we do the factorial. Understand? All right, one more, and then I'm going to be able to prove the most beautiful formula in math. Beautiful equation. It's not really a formula, it's an equation. And I'm not, look, I want you all to take away, I'm not telling you that that is the most beautiful equation in math. I'm telling you it is argued to be. Beauty is subjective, right? Right? Okay. E to the x. E to the x. Maclaurin series for e to the x. So I hope when you look at that and you think about it for a second, when we make this little table over here, nth derivative, and then over here the nth derivative plugging in 0 because it's Maclaurin, that the derivatives are going to be nice, aren't they? I mean, they're all the same. Right? The zeroth derivative of this function at x is just e to the x. And every single one of these is e to the x. All the way down. And when you plug in 0, it's e to the 0, which is 1. So these are all 1s the whole way down. Right? That makes sense? You're looking like you're not happy with that.
That just seems too easy.
The Maclaurin series for E is super clean. Okay, so look, that means when I come over to this formula, right? All of these are always what? 1, right? No matter what. So I can go straight to the sum. N equals 0 to infinity, 1 over n factorial x to the n. Now this only works because these are all the same. If these switched, then we would need to write them out first, see what they look like, see if we can kind of pick up a pattern. Now let's write this out because I want us to actually see what it looks like. What is it when we plug in 0? We get 0 factorial, which is 1, right? So 1 over 1, x to the 0 is 1, so we get 1. Plus, now we're plugging in 1, so 1 over 1, x to the 1, that's just x. Plus 1 over 2 factorial, x squared. Plus 1 over 3 factorial, x to the third. Plus 1 over 4 factorial, x to the fourth. Plus dot, dot, dot. Is this an even function or an odd function or neither? Neither, right? It contains both your odd and even powers of x, right? All right. Y'all ready? I'm so excited. So excited. All right, so now I'm going to try and prove to you that this is true. I'm trying to prove that e to the I pi plus 1 equals 0, right? That's what I'm trying to prove to you. And we said that really what I need to prove to you is that that's equal to negative 1, right? That's what I need to prove.
Is this something that we should
Oh, well, yeah, I mean, why not, right? I mean, I'm not going to ask you to prove it, but okay, you ready? Now, let's remember, this right here is e to the x, isn't it? This is the Maclaurin series for e to the x, which means that if you want to plug, like if you get on your calculator and plug in like e cubed, right, e to the third power, it'd be the same as replacing that with 3, that with 3, that with 3, that with 3, and then going out as far as you need to, right? What I'm going to ask us to do right now is to try and determine what e to the I pi is. Okay, that's what I want to show that that's negative 1. So that means the I pi is the x. Understand? Okay, let's plug it in. So according to this formula, it's 1 plus x. X is, so I pi. Okay, plus 1 over 2 factorial I pi squared. All right. plus 1 over 3 factorial I pi cubed plus 1 over 4 factorial I pi to the 4th. I'm going to go quite a few more here. 1 over 5 factorial I pi to the 5th. 1 over 6 factorial I pi to the 6th. One more. You what? Oh, you run out? Okay, you can stop at 6. All right. Now, before I proceed, let's just be clear on what I is. Do you all agree that I, by definition, is the square root of -1? That's the definition of I. Now, by that definition, what is I squared? I squared should be -1. That's the definition, right? So if you square that square root, you get what's underneath. This is the craziness of I. It's a number that when you square it, you get a negative, right? Yes? Okay, what would I cubed be? Wouldn't it just be I squared times I? So wouldn't it be that times I? So wouldn't that be just -I? You all follow? So that times I would be -I. Now, what's I to the 4th? That would be this thing times itself, right? So that squared, which would be 1. You follow me? Okay. So let's continue. What would I to the 5th be? That would be this one times another I, wouldn't it? This times I. So I could put that, but can I just put I? Right? Like that times I is just I. Now what's I to the 6th? That times I again, which is I squared, which is -1 again. Right? And then it's going to keep doing that. So that's that times I, -I. And then, I to the 7th. Then I to the 8th would be 1. So we get this cyclic thing again, this cycle happening. It starts out, right, I to the 1st power is just, well, I, isn't it? I to the 1st power is I squared is -1, I cubed is I to the 4th is 1, I to the 5th is I to the 6th is -1, so it cycles through. Ready? Here we go. Back over here. Equals 1 plus I pi plus 1 over 2 factorial. Now, when you square I pi, you square the I and the pi. So when I square the I, what do I get? I squared, -1, right? So that's going to be -1. So can I change this out here to a minus, please? Now, the I is gone, right? Because it became a -1. But you still have the pi squared. So that's going to be pi. Whoa, that's a weird pi. This is going to be pi squared. Understand? Okay, now, when we do the next one, I cubed, pi cubed, the I cubed turns out to be what? I cubed, -I, right? So this is going to become -1 over 3 pi, because I cubed is -I, right? So do you agree? I still have an I there. Yes? I have an I there, and I have a pi cubed. Yes? Okay, next one. 1 over 4. Okay, so what's going to happen when I take I and raise it to the 4th power? We're going to get 1, right? So it's not going to change anything. It's just going to be 1 over 4 factorial, and then that to the 4th was 1, and then we still have pi to the 4th. Yes? Okay. What now? What about this one? Plus, so I to the 5th, right? That's what we're going to have here. I to the 5th is I, right? So we're still going to have an I there. And it's going to stay plus, but it's pi to the 5th. All right. How about 1 over 6 factorial, I to the 6th, pi to the 6th? What's I to the 6th? -1. So minus 1 over 6 factorial. No more i's, right? Just pi to the 6th? Or wait, hold on. Yeah. just pi to the 6th. What about I to the 7th? Minus I, right? So it's going to be a minus 1 over 7 factorial. We still have an I? I pi to the 7th. What would the next one be? Plus 1 over 8 factorial. I'm going to erase this. So we did I to the 8th, which was 1, right? So we'd still have just pi to the 8th. Following me? I want to see if I can go a little bit more. What would the next one be? I to the 9th. So plus 1 over 9 factorial. I pi to the 9th. I think that's sufficient for now. Okay. Now, what do all of these have in common? They all have I. Right? Well, there's other patterns too, but do you all agree that those all have I? Yeah. And everything that I have not underlined, these do not have I. Right? They do not have I in those, in the green? So I'm going to split these up into two separate series sitting next to one another. All ready? All right, so this is equal to 1 minus 1 over 2 factorial pi squared plus 1 over 4 factorial pi to the 4th minus 1 over 6 factorial pi to the 6th, right? Plus 1 over 8 factorial pi to the 8th plus dot, dot, dot. Do y'all agree? Y'all agree with that? Now that would continue. I could keep on grabbing some more of those out there. But then plus, now the other series in blue. I pi, right? Now they all have an I in them, don't they? So why don't I factor an I out? Okay? And then what would I have left? Pi minus 1 over 3 factorial pi cubed plus 1 over 5 factorial pi to the 5th minus 1 over 7 factorial pi to the 7th. One more, plus 1 over 9 factorial pi to the 9th plus dot, dot, dot. We're almost there. Notice that these are all evens, even powers of pi, right? Even powers of pi. And these are all odd powers of pi. So, sine of x gives us all the odd powers, right? So I want to see if I can convince you of this real quick. This right here is odd powers. Could I say that that is sine of pi? So what would happen if I plug pi into this function over here? We know that we would start out with a, what? Hold on a second. N is 0. Did we get that right? 1. Did our sign start out negative? Hold on. Did it start out negative or positive? Start out positive, right? That formula is wrong. Did I write it down? Check your notes. That should have been n, not n plus 1. Just check your notes. It should have been n. I think I wrote n plus 1. It's n. Because it started positive, didn't it? Yeah, sorry, that was my oversight. This should be negative 1 to the n. This should be negative 1 to the n. Because they both start positive. But then they alternate. Okay? So let me go again. Let me try it with a fixed formula. Look, if n is 0, this is positive, right? You get 1 over 1 factorial. So 1 over 1, and then pi to the 1, right? So you get pi. Then if you plug in 1, what do you get? Negative 1 over 3 factorial pi to the 3rd. Then plus 1 over 5 factorial pi to the 5th. minus 1 over 7 factorial pi to the 7. Understand? Yes? Okay, and then what is this? This is cosine of pi plus I times sine of pi. What's sine of pi? Sine of pi. 0. This is 0. 0 times I? Gone. What's cosine of pi? Negative 1. So what have I shown? I've shown that e to the I pi is negative 1. Which checks. That's pretty cool, right? What's that? Yeah, it is a neat party trick. You can do this over the holidays. All right? So e to the I pi. Let's do another Maclaurin series. These Maclaurins are fun, aren't they? So check this out. In your book, just so you know this, on page, whoa, wrong chapter. On page 484, there is a table of common functions and their power series. First one is 1 over 1 minus x. 1 over 1 minus x. That's the one we did in 8.6. Followed by e to the x, sine x, cosine x, arctangent x, natural log of 1 plus x, and 1 plus x to the kth power. I'm just telling you it's there. I will provide you that table on the test, on the final. I'm going to give you that table. So if I tell you to find a Maclaurin series for something, you can use that table, all right? You can use that table unless I say use the formula, the Taylor series or Maclaurin series formula, all right? So let me show you an example of this. Let's find the Maclaurin series for e to the negative x squared. You know where I'm headed now, right? All right, so this function right here, we never wrote down the Maclaurin series over here for e to the x, did we? Sum n equals 0 to infinity. It was 1 over n factorial x to the n. We just proved that a second ago by going through and taking the derivatives. We said that this was a really clean formula, right? So this says if you ever want to write something, e to the negative x squared, in its Maclaurin series, then all you have to do is realize that this negative x squared here is the x in the formula. Just like I did e to the I pi a second ago. All right, so according to this, this should be sum n equals 0 to infinity of 1 over n factorial, and not x to the n, what? Negative x squared to the n. Right? Which is equal to sum n equals 0 to infinity, 1 over n factorial, negative 1 to the n times x to the 2n. So what did I do there? Separated it. So what I did is I took this right here and that. I did is negative 1 times x squared, and then I raised it to the n. And then I did the nth power on both of those. So that became negative 1 to the n and x to the 2n. And that's pretty much it. I have sum n equals 0 to infinity. I could write it like negative 1 to the n over n factorial, and then x to the 2n, like that. There it is. There's the Maclaurin series for e to the negative x squared. Okay? So, finally we get to answer a long-standing question. Find the integral from 0 to 1 of e to the negative x squared dx. So that integral cannot be done without series, and I told you that a long time ago, right? But what we can do is we can say that this is equivalent to finding the integral from 0 to 1 of its Maclaurin series.